So we're going to cover section 2.4 tonight. Like I said, next week we'll do 2.5, and then we'll start. I split up chapter 3 into 2 parts. So we'll start chapter 3 with the review of factoring. And then the following week, which will be the 24th, that's when we'll actually have our test over chapter 2. All of your assignments, and I think I mentioned this already, all of your assignments for chapter 2 from last week, and then this one tonight will be due next Monday. So they're not late or anything yet. I wanted you having time to prepare for your test so that you wouldn't have to worry about those other assignments unless you felt like doing them. So, and for you, just email me and I'll open up that one that you said you had some issues with. So, okay, we are going to talk about modeling data using linear models. And when we talk about modeling data, we are talking about coming up with an equation to represent a situation. And I know we did some of that in section 2.3 for those of you who watched that already, and we had to use word problems and come up with equations from the word problems. Here is different. We're actually going to be given data, like information, like statistics that people collected, and we're going to figure out a way to come up with an equation to represent that rather than like a word problem. Okay, so it's going to be a little bit different. But when we say that we want to fit a linear model to data, it means we're going to estimate or calculate the equation of a line. We're going to deal with lines. The equation of a line that represents or approximates the points in that data set. Okay, and I'm going to show you how to do that. So if you don't know what we're talking about yet, that's fine. We're going to learn it. Okay, so that is what it means, though, to fit a linear model to data. So here's our first example. Example 1, we've got the table below shows the number of cricket chirps in 15 seconds, and then the air temperature that goes with that information in degrees Fahrenheit. Plot this data and determine whether the data appears to be linearly related. And when it says linearly related, it means we can come up with a line that pretty much will represent the points that we find. Okay, so here's our data, and let's go on to the next thing. And I don't have that, so let me grab one of these papers so that we can go through this. And you can go along too as we're working through this here. There we go. All right, so our first point is going to be 44 chirps, which is the 44s on the bottom. So 44 and 80.5. So 44 would be about right here, and 80.5 we're going to go up to about there. Okay, so we're just going to put a point to represent that information, 44 chirps in a temperature of 80.5 degrees. Next one, 35, which would be right here in the middle, goes with 70.5, so that's going to be right about here. Okay. The next one, 20.4, is just a little bit bigger than this, and it's going to go up to 57, so that's going to be about right there. Then 33 chirps is right about here, and that's going to go up to 66, which will be about right there maybe. 31 goes with 68, so a little shorter but a little higher. Is everybody with us so far? How we're doing that? Then 35 and 72. So 35 will be right here. We're going to go up to 72. This one is 35, and so we're going to be a little bit higher than that one. Then 18.5. So 18.5 is just less than 20 here. We're going to go up to 52, which will be about right there. And 37, which will be over here a little bit closer to the 40. And 73.5. So that's going to be a little higher yet. And finally, 26 and 53. So 26 will be almost in the middle, and 53 will be probably about right there. Okay, so, and again, we don't have real super accurate grid lines here, and we don't need to. I mean, if you were really going to try and be real accurate, then you could have grid lines, but it's going to look something like that, right? Is everybody kind of seeing that as they're drawing theirs? All right. So the idea here, what we're looking at is, does this look like it's linearly related? And the answer I would say is, yeah, we could draw a line that pretty much represents that data. Now, is it exactly in a straight line? No, but we wouldn't expect that to happen. We would expect it to be basically kind of in a straight line. Okay, so yes, we would say that this is linearly related. The number of chirps per 15 seconds and the temperature, the idea is the more chirps that you hear, probably the higher the temperature is, right? The fewer chirps you hear, probably the lower the temperature is. Maybe they're just not as active when it's colder. Okay, so that's the idea there, and we're going to come back to this at various times. You'll see it later on as we go through this, or we'll refer back to this one. So there we go. I was relatively close, right? Relatively close. Pretty good. All right, so this is where they actually were, and like I said, these two are not great, but the rest of them are really pretty close. Okay, so that's what the picture actually looks like, and I made them big so you could see them pretty well. But that's, again, you can see that's linearly related, right? Okay, so the simplest way to find an equation to approximate this data is to try to eyeball a line that seems to fit the data fairly well. Then find an equation for that line based on the slope and the intercept. So we've already talked about slopes and intercepts at the beginning of chapter 2. We're going to repeat that a little bit more today. So using the table of values from the previous example, we're going to find a linear function that fits the data by eyeballing a line that seems to fit. So here's our data. And when we say eyeballing, it means we're just going to try and draw a line. We're going to try and draw a line. Oh, my computer's freaking out there. Okay, if you try to watch this video, you're probably going to have a seizure of some sort because it is flashing really badly, unless I stand here and then it doesn't flash. That's weird. Okay, so I'll just stay in the picture then. So what we would try to do is we would try to estimate a line. And so to do that, what I would probably do is pick a couple points so that we have exact values to work with. And maybe I would pick, I was going to grab the green one, but I got distracted by my flashing screen here. So I would probably pick maybe this one and maybe this one. And if I could draw a straight line as much as possible from the middle of that point to the middle of that point, let's see how well I can do. Whoa, that's not very straight, but we'll just pretend it's straight. Okay, do we see how that kind of represents the data pretty well? Okay, now the ordered pairs that we have with these 2 points, let's check that out. The ordered pairs that we have here are 44 and 80.5 for this one. Okay, so that's the ordered pair on that one, 44 and 80.5. And then the other one was, the smallest one here is 18.5 and 52. Okay, does everybody see those 2 points are the points that we chose to look at? Now, there's no magic thing. It doesn't have to be the first one and the last one. It just so happens that in this case, they kind of worked out nicely. But what you're trying to do is pick a couple points that you can shoot through exactly and try and represent the data pretty well. Okay, so what we're going to do is come up with an equation now for that line. So let's take a look at this. The first thing, if you remember, that we have to do to find the equation is we're going to use the slope formula. So m equals y2 minus y1 over x2 minus x1. Okay, and hopefully you remember seeing that. If not, you may want to go back and watch those videos. So for us, we'll call this point number 1 and this point number 2. So our y2 value is the 80.5. And that will go in right here, 80.5 minus, then the y1 value will be the 52. And that's going to go on the top. Then on the bottom, we have x2, which is going to be 44, minus x1, which is 18.5. Okay, and now I'm going to grab my calculator, and and you guys can help me out here. Oh, it's freaking out again. Let me get back in the screen. That is so weird. Okay, actually, I'll just let you guys help me out. What is 80.5 minus 52? 28.5? Okay, and then on the bottom, what is 44 minus 18.5? Is that 25.5? Okay. And then we want to go ahead and divide this. So we're going to divide it, and we're going to round off to 3 decimal places. So what do we get when we take 28.5 divided by 25.5, and we'll round off to 3 decimal places? 1 point something. Is it 118?
Yeah.
Okay, I only know that because we actually did this lesson today in my high school college algebra class. And so I knew that it was 1.118 because I remembered it. Okay, so that I didn't do that in my head. It's just I happened to remember it. It wasn't that long ago. So we've got our slope. Now, remember the next thing we need to do, we need to go back, and let me switch colors here to kind of differentiate. Well, we want to go back to our slope-intercept form, y equals mx plus b. Okay, we just figured out what m was, what the slope was. So what we're going to do is we know the slope is approximately 1.118 if we round it off. And what we need to do is we want to plug in x and y values from one of these 2 points. And it doesn't matter which point we choose, but we just want to pick one of them. So which point would you guys like to use? This one?
Yeah.
Okay. So that means the x value that we're going to put in is 18.5. So that's going to go here where the x was, 18.5. And the y value we're going to put in is the 52. That's going to go over here. And then our goal is we want to figure out what this b is. That's the one we don't know yet. So does that make sense? Now we have an equation. We can figure out what b is. So we're going to start out with 52. Can somebody help me out? What is 1.118 times 18.5?
20.68.
20.68. Okay, plus b. And then what do we have to do now to get this b by itself?
Minor the 20.68.
Correct.
Both
So,
sides.
yeah, so it's perfect. Subtract 20.68 from both sides of our equation. So we're going to have b here, and then here we're going to have, I think that's going to be 31.32. Is that correct? Just if we subtract that, 52 minus 20.68. I know I've got calculators out there. That's right?
Yeah.
Okay. So this is our b value that we were looking for. We already knew the m value from up here. So that means our equation is y equals the m, 1.118. And we're just following y equals m, 1.118 times x, and then plus b, and b is 31.2 or 31.32. Sorry. Okay, and that is our equation of this line that I attempted to draw to represent these points. Are all the points directly on the line? No, but it's an estimate of where those points are. Does that make sense? So it's very rarely ever going to be a perfectly straight line. So this line is, I mean, the points are very rarely ever going to be in a perfectly straight line. So this line is just an estimate of our data. We would say it's approximately on this line somewhere. Okay, so that is how we that's how we come up with a line from our data. We're going to have to kind of eyeball that line that we think fits it pretty well. Try to use a couple points, and again, it could be some points in the middle, it could be points on the end, it doesn't matter, but you're going to want to probably use 2 points that you have data for from your table, and then you use that to find the slope and then find the intercept, and that's how you get your line. Okay, just like we did, I think it was probably in section 2.2. I can't remember for sure, but I think that's the section that was in. Okay, any questions on that? Now I'm stuck. I got to stay in this picture, otherwise it starts flashing like crazy. So just keep my arm in there. Any questions on that? Okay, so make sure this is written down because we're going to come back to this later on. Okay, so make sure that's written down. In fact, I'm going to write it in the corner here so that I don't forget it. Y equals 1.118x plus 31.32. All right, so we've got that taken care of. And we want to talk next about two different types of estimation, or two different types of prediction. And the first type that we have is called interpolation. I know that sounds like a funny word, but the beginning of that word is in, right? In. And that's kind of the important part. In. It's predicting a value that is inside the domain and the range of our data. The domain, remember, is the x values that we saw from our data, and the range is the y values that we saw from our data. So we're looking for something inside the data, basically, okay, and predicting something inside the data. So, for instance, if I was doing some sort of a project and I gathered data from the last 10 years of, let's just say, population of Monette, or actually, let's say I gathered it from 10 years ago and from 5 years ago and from this year. Okay, so I have three different values, and I could make a line that represented kind of those three values. If I was going to estimate the population of Monette from 2 years ago using that data, that would be interpolation because it's inside of the stuff that I gathered, right? That's interpolation. Now, the other one is extrapolation. That's if I would take this data and this line and I would predict into the future what the new population would be outside. So like 5 years from now. Does that make sense? That I haven't collected any data around that. I'm just predicting into the future. That would be extrapolation. Okay, it's like we're trying to go outside of what we've been able to gather information about. It could be also in the past. If I wanted to go 20 years in the past using the data that I had collected, that would be extrapolation also. Okay, so anything that's outside of that information, the highest and lowest information that we've gathered, would be extrapolation. So that's predicting a value outside of our domain and range. So let's look at a couple examples of this. Example 3, part A, would predicting the temperature when the crickets are chirping 30 times in 15 seconds be interpolation or extrapolation? And then we're going to make the prediction and discuss if it is reasonable. That's where we're going to use our equation. So let's go back to our picture. 30 times in 15 seconds. Well, let's look at this. We have data that runs from here to here when we talk about chirps, and they're asking us to estimate here. Do you think that would end up being interpolation or extrapolation? That would be, and I heard several people say it, but I'm not sure if everybody said it. That is interpolation because that is, we have values all the way from 18 to 44, right? And that 30 falls in that range. So that's interpolation. We have data around this 30. Does that make sense? Okay. Now, what we're supposed to do, they want us to go ahead and use our formula to figure this out. Well, 30 is the number of chirps. That was our x. These were our x's down here, and these were our y's up here. So we would have y equals 1.118 times 30 plus 31.32. And actually, you can type that all into your calculator all at once. If somebody could do that for me, what do we get for a temperature and a predicted temperature if we are hearing 30 chirps every 15 seconds?
64.86.
64.86. So about 65, right?
Yeah.
Okay. And does that seem reasonable with what we're seeing on our graph, that it would be somewhere in this range right here? Yeah, that seems pretty reasonable, doesn't it? Now, we don't have anything right around that area, but it's, if we had something there, it seems like it would be about in that spot, right? So yeah, that seems pretty reasonable. And usually interpolation will be pretty reasonable values because we have values all around it. Okay, let's go to the next one, which is B. And for B, we're going to predict the number of chirps chirps crickets will make at 40 degrees by interpolation or extrapolation, or will that be interpolation or extrapolation? And then make a prediction and discuss if it's reasonable. So let's go back to our table again. This time they're asking us about 40 degrees. What we have as the lowest side for temperature is right there, and the highest side is about right there. So would you consider that interpolation or extrapolation? That one's extrapolation because it's outside of anything we have data for. Does that make sense? We only have data down to a little bit above 50 degrees. Okay, now does that mean we can't predict? No, we can still predict, but it's extrapolation. So let's predict. Now this time we're given the 40, and remember that's the y value. Okay, so this time we're going to have 40 equals 1.118 times x plus 31.32. So we've actually got to do some math here to solve this one. Can't just type it into a calculator. What will we do first? Because our goal is to get this x by itself. Yes, whoever said it, subtract 31.32 is correct. So this will cancel, and this I think is going to be 8.68. If you guys could double check me on that math, I would appreciate it, because sometimes when I do things in my head, it doesn't always come out right. Are we good with that number? Okay, I saw one nod at least. So then what else do we have to do to get the x by itself?
Divide the number by
Yep.
the x.
Yep.
on both sides.
Take the 8.68 and we're going to divide both sides by this 1.118. And that's going to cancel. We're going to get x. And what do we get approximately for this when we divide it?
7.763.
So we'll say about 8. Okay, I mean, this is a number of chirps. We're not going to have 7.5 chirps or anything like that. So in this case, we'll probably just go with about 8. And does that seem reasonable? Well, that would be over here somewhere. If we kind of extend our line, does that seem reasonable? Probably. I mean, because the idea is as it gets colder, the idea is as it gets colder, we hear less chirps, right? So it probably is reasonable. But the one thing you have to be careful of is in that extrapolation, sometimes it's not reasonable. Like if I kept going backwards here, do we see that eventually I would get to negative amounts of chirps? Would that be reasonable? To have a negative amount of cricket chirps? No, because how is that even possible? You couldn't do that, right? Or if I had a whole bunch of chirps and I got a temperature that was like 200 degrees, would that be reasonable? Probably not, because the crickets are probably dead at 200 degrees. At least I would be in pain at 200 degrees, so I'm guessing they would be as well. Okay, so that's where extrapolation, when we get outside, either high or low, we have to be a little bit careful about our predictions. Okay, does that make sense? Because the data that we collect kind of shows it works for this amount of space, but if we get outside of that, it may not, that model that we come up with may not work anymore. Okay, does that make sense with the difference between extrapolation and interpolation? All right, let me erase my red markings all over the place here. All right, let's see, we did A, we did B. All right. And we already did 2 like this, so I don't think we need to do this one. But it would just be a matter of put 20 into our equation, right? The number of chirps was the x value, so we would just plug the 20 in, type it into our calculator, we get an answer. Okay? So, oh, and I have it here. It was 54 degrees if we use our equation. All right, so another thing that you can do is fitting lines with technology. And when we say fitting lines with technology, we're talking about there is a method, a formula basically, a statistical technique for fitting a line to data that minimizes the differences between that line and the data values. Rather than just guessing where the line should be, there is a way to figure out where the best line would be. Okay? This technique is called the least square regression and can be computed by many graphing calculators. So if you have a graphing calculator, it will do that. Spreadsheet software like Excel or Google Sheets, statistical software, and many other web-based calculators. in this class, I'm not going to make you go out and buy like an $80 calculator to do these. So we're not going to worry about that. We're going to use some of the information that we could get from the calculators, but we're not going to go through the process of how would we find it with the calculators. Okay. I don't see any reason to make you guys go out and make that investment, and you may or may not use that calculator after this class. So, but here's what happens when we do use a calculator, graphing calculator in this case. A regression was run to determine the relationship between the years X since 2010 and the amount of money in millions spent on apps, which is Y, in the United States. The results of the regression are right here. So notice when you see this, it doesn't say Y equals MX plus B, right? But it looks really similar to that, doesn't it? Y equals A times X plus B. This is the equation of a line. They're giving us the line of regression, it's called. This is the best line that would fit the data the best. So they're saying the A value should be this 1.7527 and so on. The B value should be 14.672 and so on. And this is some other information that we'll talk about a little bit later. So what I want to let you guys know about here is, if we want to have the equation using this information, what we would do is we'd say our equation is Y equals, then we need the A value. So we usually do like 3 decimal places. So 1.753 if we rounded that off. And then the X. And then the B value, again, to 3 decimal places, 14.673. And this would be our equation using the information from this regression. This is a picture straight from a calculator, actually, because this is exactly how those calculators look. But that's what we would do. We would write down the equation, just like what we had up there, in the same form, but they would give us the numbers. We just have to write them down as the formula. Okay, does that make sense? Now, you're not going to have to do this part, but I will give you sometimes a picture that looks like this, and you just need to be able to take that information and write it out as an equation. Use this to predict the amount of money spent on apps in 2020. Okay, so we're going to use this equation that we just wrote down. But here's where we have to be careful. X is the number of years since 2010. Okay? If we want 2020, what should our X value be?
10.
10, because it's 10 years after 2010, right? Does that make sense? So we're just going to take this equation and we're going to plug in a 10. So 1.753 times the 10 plus 14.673. And if somebody, again, this is when you're typing it in like this, you can just type that whole thing into your calculator all at once. So if somebody could do that for us, what do we get for that number? And you guess somewhere 32 point something. Is that right?
32.203.
32.203?
Yeah.
Okay. And actually, remember, that is in millions of dollars. So this is over $32 million is what this linear regression is estimating will be spent on apps in 2020. Now, could that have been true? Well, probably. A lot of people have phones now, and they probably spend money on apps at various times. So, and it probably is just going to keep going because people have more and more people have phones, right? And they probably want to have apps, and not all of them are free. So that's just the way it is, right? So, does that make sense? How we would use this information to come up with the equation, and then we can use the equation to answer the question that they give us. Okay. Anybody need that to stay up there any longer? All right. So the next thing we want to talk about is, again, those calculators or computer software. A lot of times when you get that information for the line of regression or the line of best fit, they will also give you what is called a correlation coefficient. And the correlation coefficient is a measure of how closely the line fits the data. So you remember how our line, the data was pretty close to it, but it wasn't directly on the line. that correlation coefficient tells you if it's directly on the line or how far off the line all those points are. Okay, so if we go back, the correlation coefficient is actually this R value. And notice our R value is 0.986, which is pretty close to 1. We're going to talk about what happens when it equals 1. But that means it's pretty close to being in a straight line. Okay, the closer it is to 1, the closer it is to being in a straight line. So let's take a look at some information about the correlation coefficient. It's abbreviated with an R, as we just saw on the calculator picture. It's always going to be between -1 and +1. Always. So if the R value is greater than 0, that suggests a positive or an increasing relationship. In other words, that line that you're estimating with is going to have a positive slope. So as one thing increases, the other thing also increases. That's the idea there. If the R value is less than 0, that suggests a negative or a decreasing relationship. In other words, as the one value gets bigger, the other value is going to go down. It's going to decrease. Okay, so that's the difference between R being positive or R being negative. Right? I'm going to actually talk about this one first. And I've got some issues with my thing here. There's 3 lines there. Okay, the closer the value is to 1 or -1, the less scattered the data is. In fact, if it is 1 or -1, that means the data is perfectly on a straight line. And they all fit exactly on the line if you have a 1 or a -1. A +1 just means it's perfectly a straight line going up. -1 means it's perfectly a straight line going down. Okay? Then, the closer it is to 0, the more scattered out the data will be. So if you get close to 0, that means the line probably doesn't fit the data very well because the data is all kind of spread out. Okay. So let's take a look at some examples of correlation coefficients. I want to look at this middle row first because notice this one has a correlation coefficient of 1. This one is also a correlation coefficient of 1. This one is 1. This one doesn't have one. I don't know if it would be 0 or just non-existent. But notice 1 doesn't mean they all look the same, but what it does mean is they're perfectly in a straight line and they all are increasing from left to right. And then here's another one that's also perfectly 1. Notice about the -1s. Decreasing, perfect straight line. Decreasing, straight line. Decreasing, straight line. Straight line. So the -1 doesn't tell you how fast it's decreasing. The +1 doesn't tell you how fast it's increasing. It just tells you it's in a straight line. Okay, and it's increasing or it's decreasing. Then we've got some other ones. Notice the 0.8, pretty close to 1, and you can definitely see the upward trend, but notice how it's more spread out, data points. 0.4, you can still kind of see that upward trend, but it's more blobbish and more spread out. You get to 0 and it's just kind of like a bunch of stuff all over the place. And then you got the -0.4 and the -0.8 kind of similar to the positive ones, right? You also can get zeros if you have some other sort of random shapes. Like this is like a squiggly type shape. You've got a box, a diamond, a smiley mouth. I don't know what that is. I don't know what that is either. Circle, 4 separate boxes, blobs, I mean. So those would all be correlation coefficients of 0 also, because does it make sense a line is not going to represent any of these very well or at all? They just do too many other weird things. I'm not going to give you any of these, but you're going to see stuff like this in your homework and on your tests and stuff. So, and that's the end. Okay. Do we have any questions on this screen before? It's freaking out again. Do we have any questions on this screen at all before we get out of here for the evening?
Yeah.
He's like, nope, we're ready to go. Let's get out of here. Okay. So you do have, remember, don't forget, you've still got 2, 1, 2, 2, and 2, 3. If you haven't already done those previously. If you have, great. You don't have them anymore. And then just this one in addition with 6 problems. Some of them, again, might have multiple parts to the problem, but and again, don't be afraid to email me if you get stuck or have questions. Don't be afraid to ask each other. Like I said, the homework, yes, you get graded for it, but it's to help you prepare for your test and to try and learn as you go. Okay? So I'm not, unless you're just copying from somebody and don't get it at all, that would be cheating and not worth it. But the whole point of it is so that you're getting practice and getting ready for your tests. Okay?